Hello, I'm Robert Miles. Welcome to this recording of the Alignment Newsletter podcast. This is newsletter number 135, 5 Properties of Goal-Directed Systems, published on the 27th of January 2021 by Rohin Shah. Highlights. Link, Literature Review on Goal-Directedness by Adam Shimi et al., summarized by Rohin. This literature review on goal-directedness identifies 5 properties that should be true for a system to be described as goal-directed. 1. Restricted space of goals. The space of goals should not be too expansive, since otherwise goal-directedness can become vacuous. See Newsletter 35. For example, if we allow arbitrary functions over world histories with no additional assumptions. 2. Explainability. A system should be described as goal-directed when doing so improves our ability to explain the system's behavior and predict what it will do. 3. Generalization. A goal-directed system should adapt its behavior in the face of changes to its environment such that it continues to pursue its goal. 4. Far-sighted. A goal-directed system should consider the long-term consequences of its actions. And 5. Efficient. The more goal-directed a system is, the more efficiently it should achieve its goal. The concepts of goal-directedness, optimization, and agency seem to have significant overlap, but there are differences in the ways the terms are used. One common difference is that goal-directedness is often understood as a behavioral property of agents, whereas optimization is thought of as a mechanistic property about the agent's internal cognition. The authors then compare multiple proposals on these criteria. 1. The intentional stance says that we should model a system as goal-directed when it helps us better explain the system's behavior, performing well on explainability and generalization. It could easily be extended to include far-sightedness as well. A more efficient system for some goal will be easier to explain via the intentional stance, so it does well on that criterion too. And not every possible function can be a goal, since many are very complicated and thus would not be better explanations of behavior. However, the biggest issue is that the intentional stance cannot be easily formalized. 2. One possible formalization of the intentional stance is to say that a system is goal-directed when we can better explain the system's behavior as maximizing a specific utility function relative to explaining it using an input-output mapping. See the link Agents and Devices, a Relative Definition of Agency from Newsletter 22. This also does well on all 5 criteria. 3. AGI Safety from First Principles from Newsletter 122 proposes another set of criteria that have a lot of overlap with the 5 criteria above. And 4. A definition based off of Kolmogorov complexity, like the one put forward by Vanessa Kosoy, works well, though it doesn't require far-sightedness. Rohin's opinion. The 5 criteria seem pretty good to me as a description of what people mean when they say that a system is goal-directed. It's less clear to me that all 5 criteria are important for making the case for AI risk, which is why I care about a definition of goal-directedness. In particular, it doesn't seem to me like the explainability property is important for such an argument. See also this comment, which is a link to a comment from Rohin Shah on the Alignment Forum post, "Coherence arguments do not imply goal-directed behavior." Note that it can still be the case that as a research strategy, it's useful to search for definitions that satisfy these 5 criteria. It's just that in evaluating which definition to use, I would choose the one that makes the AI risk argument work best. See also link Against the Backward Approach to Goal-Directedness. Section Technical AI Alignment. Subsection Iterated Amplification. Link Factored Cognition Sequence by Raphael Harth, summarized by Rohin. The factored cognition hypothesis from Newsletter 36 informally states that any task can be performed by recursively decomposing the task into smaller and smaller subtasks until eventually the smallest tasks can be done by a human. This sequence aims to formalize the hypothesis to the point that it can be used to argue for the outer alignment of, idealized versions of, iterated amplification from Newsletter 40 and debate from Newsletter 5. The key concept is that of an explanation or decomposition. An explanation for some statement S is a list of other statements, S1 to Sn, with the statement, quote, "The list of statements S1 to Sn implies S," end quote. A debate tree is a tree in which for any given node n with statement S, the children of n form an explanation, decomposition, of S. The leaves of the tree should be statements that the human can verify. Note that the full formalism has significantly more detail. For example, a concept of the difficulty for the human to verify any given statement. We can then define an idealized version of debate, in which the first debater must produce an answer with associated explanation, and the second debater can choose any particular statement to expand further. The judge decides the winner by evaluating whether the final statement is true or not. Assuming optimal play, the correct, honest answer is an equilibrium as long as, quote, "For every question, there exists a debate tree for the correct answer where every leaf can be verified by the judge." This is called the ideal debate factored cognition hypothesis. The idealized form of iterated amplification is HCH, see newsletter 34. The corresponding factored cognition hypothesis is simply, quote, "For every question, HCH correctly returns the correct answer," end quote. Note that the existence of a debate tree is not enough to guarantee this, as HCH must also find the decompositions in this debate tree. If we imagine that HCH gets access to a decomposition oracle that tells it the right decomposition to make at each node, then HCH would be similar to idealized debate. HCH could of course simply try all possible decompositions, but we're ignoring that possibility. The decompositions that we rely on should reduce or hide complexity. Is the HCH version of the factored cognition hypothesis true? The author tends to lean against, more specifically that HCH would not be superintelligent, because it seems hard for HCH to find good decompositions. In particular, humans seem to improve their decompositions over time as they learn more, and also seem to improve the concepts by which they think over time, all of which are challenging for HCH to do. Rohin's opinion. I enjoyed this sequence. I'm glad to see more analysis of what is and isn't necessary for iterated amplification and debate to work, as well as more theoretical models of debate. I broadly agreed with the conceptual points made, with one exception. I'm not convinced that we should not allow brute force for HCH, and for similar reasons I don't find the arguments that HCH won't be superintelligent convincing. In particular, the hope with iterated amplification is to approximate a truly massive tree of humans, perhaps a tree containing around 2 to the 100, about 1 times 10 to the 30 base agents/humans. At that scale, or even at just a measly billion, 1 times 10 to the 9 humans, I don't expect the reasoning to look anything like what an individual human does, and approaches that are more like brute force seem a lot more feasible. One might wonder why I think it's possible to approximate a tree with more base agents than there are grains of sand in the Sahara Desert. Well, a perfect binary tree of depth 99 would have 1 times 10 to the 30 nodes. Thus we can roughly say that we're approximating 99 depth limited HCH. If we had perfect distillation, this would take 99 rounds of iterated amplification and distillation, which seems quite reasonable. Of course, we don't have perfect distillation, but I expect that to be a relatively small constant factor on top, say 100 times, which still seems pretty reasonable. There's more detail about how we get this implicit exponential time computation in the post Factored Cognition from newsletter 36. Subsection Mesa Optimization. Link Defining Capability and Alignment in Gradient Descent by Edward Harris, summarized by Rohin. Consider a neural network like GPT-3 trained by gradient descent on, say, the cross-entropy loss function. This loss function forms the base objective that the process is optimizing for. Gradient descent typically ends up at some local minimum, global minimum, or saddle point of this base objective. However, if we look at the gradient descent equation, theta equals theta minus alpha g, where g is the gradient, we can see that this is effectively minimizing the size of the gradients. We can think of this as the mesa objective. The gradient descent process, with an appropriate learning rate decay schedule, will eventually get g down to 0, its minimum possible value, even though it may not be at the global minimum for the base objective. The author then proposes defining capability of an optimizer based on how well it decreases its loss function in the limit of infinite training. Meanwhile, given a base optimizer and mesa optimizer, alignment is given by the capability of the base optimizer divided by the capability of the mesa optimizer. Since the mesa optimizer is the one that actually acts, this is effectively measuring how much progress on the mesa objective also causes progress on the true base objective. This has all so far assumed a fixed training setup, such as a fixed dataset and network architecture. Ideally, we would also want to talk about robustness and generalization. For this, the author introduces the notion of a perturbation to the training setup, and then defines capability robustness and generalization, and alignment robustness and generalization, based on whether the optimization stays approximately the same when the training setup is perturbed. It should be noted that these are all definitions about the behavior of optimizers in the infinite limit. We may also want stronger guarantees that also talk about the behavior on the way to the infinite limit. Subsection Learning Human Intent. Link Imitating Interactive Intelligence by the Interactive Agents Group et al., summarized by Rohin. While existing work from newsletters 11 and 103 has required agents to follow natural language instructions, it may be the case that achieving AGI requires more interactivity. Perhaps we need to train agents to both give and follow instructions, or engage in a full dialogue to accomplish tasks in a 3D embodied environment. This paper makes progress on this goal. The authors introduce a 3D room environment in which agents can interact with objects and move them around, leading to a combinatorial space of possible high-level actions. So far, the authors have only worked on question answering, for example, what is the color of the chair, and instruction following, for example, please lift up the purple object, but they hope to eventually also work on dialogue and play. They collect demonstrations of games between humans, in which one human is given a goal and then is asked to give a natural language instruction. The other human sees this instruction and must then execute it in the environment. The authors then use various kinds of imitation learning algorithms to learn a policy that can both set instructions and execute them. They also train models that can evaluate whether a particular trajectory successfully completes the goal or not. The authors show that the learned policies are capable of some generalization. For example, if during training they remove all rooms containing orange ducks, but don't remove other orange objects and other colors of duck, the resulting policies are still able to handle rooms containing orange ducks. If you want to read more, you can read the paper Probing Emergent Semantics in Predictive Agents via Question Answering. Subsection Robustness. Link Evaluating the Robustness of Collaborative Agents by Paul Knott et al., summarized by Rohin. Assuming a well-specified reward function, we would like to evaluate robustness of an agent by looking at the average reward it obtains on a wide scenario of plausible test time inputs that it might get. However, the key challenge of robustness is that it's hard to specify the test distribution in advance, and we must work with the training distribution instead. This paper, on which I'm an author, proposes measuring robustness using a suite of hand-designed unit tests. Just as a function is tested by having the programmer write down potential edge cases and checking for the expected behavior, AI developers can come up with a set of potential edge case situations, especially ones not likely to arise during training, and check whether the agent's behavior in these situations works well or not. Intuitively, since these unit tests are created separately from the training process, they may not have the same spurious correlations that could be present in the training data. Thus, they can serve as an evaluation for the robustness of the agent. The authors built a test suite for Overcooked from Newsletter 70 and use it to evaluate several techniques aimed to improve the robustness of agents trained to collaborate with humans. For example, one technique is to start each episode from a state sampled randomly from a dataset of human-human gameplay so that the agents learn how to handle a broader diversity of states. This technique decreases the average validation reward, and if that's all we look at, we would conclude that it did not work. However, the technique also increases performance on the unit test suite, suggesting that in reality the technique does include robustness, though it comes at the cost of reduced performance when playing with the particular set of partners that make up the validation distribution. Section AI Governance. Link Bridging the Gap, the Case for an Incompletely Theorized Agreement on AI Policy by Charlotte Stix et al., summarized by Rohin. Like several past papers, see newsletters 90, 44, and 105, this paper argues that the differences between the near-term and long-term communities are probably exaggerated. Collaboration between these communities would be particularly beneficial since it could prevent the field of AI policy from becoming fragmented and ineffectual, which is especially important now while the field is nascent and there is political will for AI policy progress. The authors propose the notion of an incompletely theorized agreement in order to foster this sort of collaboration. In an incompletely theorized agreement, the parties agree to suspend disagreement on some thorny theoretical question in order to coordinate towards a shared pragmatic purpose. Such agreements could be used to set aside relatively unimportant disagreements between the two communities in favor of pursuing goals that both communities care about. For example, we could imagine that such an agreement would allow both communities to push for more and better reflection by AI researchers on the impacts of the systems that they build, or to enable action that ensures we preserve the integrity of public discourse and informed decision-making, for example by regulating AI-enabled disinformation. Rohin's opinion. I'm certainly on board with the goal of working together towards shared goals. That being said, I don't fully understand what's being proposed here. How exactly is an incompletely theorized agreement supposed to be made? Is this more of a shared ethos that gets spread by word of mouth, or is there a document that people sign on to? If there's a document, what goes into it? Who would agree to it, and how binding is it? I'd be excited to see more work fleshing out these concrete details, or even better, actually causing such an agreement to exist in practice. This concludes Alignment Newsletter number 135. For more information, you can go to rohinshah.com/alignment-newsletter, where you can find all of the previous newsletters and also a spreadsheet of all of the papers and summaries that have ever been featured. Thank you for listening.